Welcome back. In this video, we are going to solve example 5.3 that is taken from chapter number 5 torsion and book name is Mechanics of Material by R.C. Hibbeler, ninth edition. So statement is the pipe shown in figure 5-12A has inner diameter of 80 millimeter and outer diameter of 100 millimeter. If its end is tightened against the support at A using a torque wrench at B, determine the shear stress developed in the material at the inner and outer wall along the central portion of the pipe when 80 Newton force are applied to the wrench. So you can see this is pipe clear that is tightened against this support at A using this wrench, and 80 Newton load is applied this at this wrench, which create torque at point B is in clockwise direction. So you have to determine the inner and outer radius of this pipe, the shear stress developed. Clear? So let's start with the solution. So you can see that these are non-collinear force. They are not lying at the same point, but they are acting in the same plane. So this will produce a torque, and this torque will be equal to 80 multiplied by total distance between them. This will be the torque, and that will be in Newton into millimeter. Now what we will do is that for our analysis purpose we can section this pipe at any length. Clear? We will section it over here and we will determine the torque. This is the clockwise torque, so here you will have anti-clockwise torque at point C. Clear? So we will draw the free body diagram. I have already drawn here, only I have to show that this will be TC. Clear? Now we'll apply equation of equilibrium that sum of all moments about y-axis must be equal to 0, and taking the counterclockwise torque is taken as positive. So TC, which is counterclockwise, so I can write it as TC, clear, plus minus this 80 multiplied by 0.3 in meter plus 0.2 will be equal to 0. Now this TC will be equal to 80 multiplied by 0.5. Clear? And when you calculate it, so 80 multiplied by 0.5 will give you 40. So I will write 40 and the unit will be Newton into meter. Now you have this torque, and this torque will be throughout same when you cut it along the length of pipe at any length. And we know that shear stress is equal to T into rho divided by C, while rho is greater or equal to 0 and less or equal to radius C. As we have been given the inner diameter and outer diameter, so inner diameter DI is 80 millimeter. So from here C inner will be 80 divided by 2, which is 40 millimeter, and in meter it will be equal to 0.04 meter. Same is the case, you have outer diameter which is 100 millimeter, and DC outer, which is the maximum radius, C outer will be equal to 100 divided by 2, which is 50 millimeter, and I can write it as 0.05 meter. Now put rho is equal to inner radius CI is equal to 0.04 meter, where you want to find the shearing stress. So shearing stress will be equal to T into CI divided by J. Clear? And what is J? So J is polar moment of inertia, and for this hollow rod it will be equal to pi by 2 C outer power 4 minus C inner power 4. So we will calculate it. J will be equal to pi by 2 multiplied by C outer is 0.05 power 4 minus C inner is 0.04 power 4. So we will solve this. Let's calculate it. 0.05 power 4 minus 0.04 power 4 will give you this, multiply by multiply by 3.1417 divide by 2 will give you 0.123455796. So I can write it as 5.796 into 10 raised to power minus 6, and unit will be meter power 4. Now you have the value of J, just plug it in. So torque is 40 Newton into meter, C is 0.04 meter, divided by J is 5.796 into 10 raised to power minus 6, and when you calculate it, it will be equal to 0.276 megapascal. Actually, you will get 0.276 into 10 raised to power 6 Pascal, and when you convert it, you will get this value. So here we can see that shearing stress, we can also write at inner shearing stress is 0.276 megapascal. Now for outer radius, C naught is equal to, when rho is equal to outer radius is equal to 0.05 meter, so we will have outer shearing stress will be equal to T into C naught divided by J. So T is 40, outer radius is 0.05 divided by J is 5.796 into 10 to the power minus 6. So when you solve this, you will get outer radius. Let me calculate it. 40 multiplied by 0.05 divide by, let me take divide by, already we have the answer that is shown over here. Okay, that is not shown over here. Let me take it. Okay, let's divide it by 5.796 into 10 raised to power minus 6 here, and you can see you have the value is equal to 345,065.562, and when you solve convert it into megapascal, this will be in pascal. So T outer will be 1 2 3 4 5 6, it will be 0.345 megapascal. And these two, this value which is an inner shear stress and this is the outer shear stress, these are the answer of our this question. Now what if you look at this was the shearing stress at this point. So if you take this section AC and or the cross section at AC, I have drawn over here at this portion, on this left side portion, the torque was counterclockwise. So in order to balance it on in portion AC, it will be clockwise. So I have represented this torque as clockwise. And if you want to represent the stress at this outer radius, let me show you over here by using this orange color. This is the outer radius and this is the inner radius. So why I have taken the outer radius at this to show how these stresses act at representative point. Let this is point D and this is your point E. Clear? On the cross section, we will first view the cross section from the front of segment CA of the pipe. So this is segment CA of the pipe. Clear? And the resultant internal torque at acting on it is this T. So you can see that due to this torque, the shear stress at point D will be this, which is equal to tau D, or that is equal to T outer, and this shearing stress is tau E, that is T inner. Clear? And the direction, if I take this smaller element at the outer surface and I have shown over here, so what will be the shear, what will be the direction of shear stress? So it will be like this. This is your point. For example, if you draw the backward side, so this will be your shear stress at point D, and that will be equal to tau D tau d is equal to how much? 0.345 megapascal. Now for this TE, you can see it is at the inner surface. So you will be having a shear stress at this point will be like this. This is upward because you can see the shearing due to this torque. The shear stress will be in upward. So this is tau E. And here this will be like this. And if you take the backward side, so it will be like this and this. So this is your tau E, which is equal to inner with 2.7276 megapascal. So this is the representation of shear stress at the inner and outer position of this pipe at the central portion of the pipe. And that was all about this example 5.3. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.